Hello, and welcome to the second episode of this series on the black hole information paradox as part of the Cambridge Festival. Today, we will discuss the return of the Susskind. I'm Roger de Belsunce.
And I'm Goncalo Regado.
And we're PhD students at the University of Cambridge. In this episode, we're interviewing Ahmadain, who's a researcher at Cambridge and an expert on this topic. Hi, Ahmed. Thanks for being here and trying to shed some light on the black hole information paradox.
Thank you, guys. Hi, Roger. Hi, Goncalo. It's great to be here. Great to be part of this year's Cambridge Science Festival.
Let's get on with it. I'm really excited for the next hour. So,
Same here.
Amber, in the previous episode, we have learned about the paradox that results from the Hawking radiation. Could you perhaps, just to bring everyone to the same page, give a brief summary of the previous session and maybe outline what's the central idea of today?
Absolutely. So briefly, before Stephen Hawking came along in the mid-1970s, it was believed that everything that falls into a black hole is doomed. Everything that falls into a black hole has no chance of ever getting out again. Right? Not even light, matter, everything, right? Anything that crosses the boundary of a black hole never has a chance of getting out again. It can only fall to the center of the black hole, to singularity. So black holes were believed to have no temperature whatsoever and no entropy. However, Stephen Hawking, in a very astonishing result, showed us by some very sophisticated and clever calculation that black holes radiate. In other words, stuff has a chance that goes into a black hole, has a chance of coming out again. And the black holes have temperature. And of course, that was very surprising to the physics community. And it actually has posed and still poses a very challenging problem what we call the black hole information paradox, which we will learn about in this lecture. And we'll also learn about perhaps there's a way out using the holographic principle of space-time that provides a way out of the black hole information paradox. And this is hopefully what we will learn throughout the lecture.
Okay, let's try to understand how serious this problem actually is. So perhaps it's a good idea to rewind for a second and take a deeper look and closer look into the information paradox. So let's start with black holes. What is a black hole?
Okay, so quite simply, black holes have been predicted, right, as solutions to the Einstein's theory of general relativity, right, which Einstein introduced in 1915. So they have been predicted, at least mathematically, as a result of his equations, the equations. But physically speaking, black holes are regions of space and time, where there's an extreme gravitational field, very, very, very extreme gravity, right? Everything is pulled around. That's what physically a black hole is, right? And why should we believe in the existence of black hole? Well, first of all, the Albert Einstein's theory of general relativity has been tested numerous times over more than a decade now. But even and more importantly, although we cannot directly see black holes because even light does not escape a black hole, there have been ways where black holes have been observed and detected indirectly. One of them is how they affect their surrounding space, the stars around them, the planets around them, and more recently, gravitational waves caused when they emerge. And as we see on the screen right now, we see even a picture of a black hole. This is one of the most recent pictures of a black hole ever taken. And on the right-hand side, we see the gravitational field of our sun, right? And then a neutron star, which is more massive than a sun and has more mass per unit area, and then a black hole. This length of the neck is what we actually describe the strength of the gravitational field. You can see the black hole is a very, very, very long neck. That is a description, a representation of how strong the gravitational field of a black hole is. So black hole really, they are very destructive machines. They destroy anything that crosses their event horizon, and anything that crosses the boundary of the black hole, which we call an event horizon, is basically removed from existence, is removed from the universe, but is not removed from existence. And that's a very important point. Although that anything that goes through a black hole becomes hidden from someone sitting outside the black hole. So think of a hypothetical observer, someone sitting in a black hole. It's just a hypothetical external observer. The stuff that goes into a black hole is hidden, becomes inaccessible, but it is not removed completely from existence. And this is a very important point. It's still there inside the black hole, right? And it's just that we cannot reach it. And that's a very important point to mention, and it's going to play a key role later in this lecture. Also, it's important to mention that black holes are regions have a very unusual feature. Some particular feature, which is really odd and unusual about black holes, which again is going to play an important role in our discussion in our lecture today, is that it doesn't really matter from the perspective of this external hypothetical observer, right? To know exactly what stuff goes into the black hole. What exactly is the stuff that goes into the black hole? It turns out that all that you need to know about a black hole is the mass, only three properties: the mass of the black hole, the electric charge of the black hole, which is like, think of the electric charge of an electron, and the angular momentum of the black hole, how fast the black hole basically rotates, if it rotates. These are the three properties that, from the perspective of someone sitting outside the black hole, that is all there is. That's all you need to know. If you know these three properties of the black hole, you know everything that's inside the black hole. This odd feature goes by the name of a no-hair theorem. This is known in the physics literature as the no-hair theorem. If you know all the properties, deep properties of the black hole, then you know everything about the black hole. And of course, as we will see later, black holes form from a collapse there are black holes basically form in our universe from stellar collapse, and we will get to that point, but it's just important to keep that in mind. The last thing I'll end with is that black holes were thought to have zero temperature and have zero entropy. What is entropy? We'll find out.
Well, perhaps we should take it from there. You just mentioned this concept of entropy. Can you perhaps explain this concept to the audience and what it means for our everyday life?
Okay, thank you, Goncalo, for the question. Absolutely. So entropy is really one of the most fundamental concepts in all of physics. It's also one of the most difficult to probably explain, and one of the easiest as well to explain. So we'll see why it's the easiest, most difficult. But let's start slowly. So something we can quickly sort of explain what the concept of entropy is. If you put an ice cube into a hot bowl of water, what happens? Well, the ice melts, of course, right? The ice melts. If we don't really see the ice cubes that you put there spontaneously form again after they have melted, right? We don't see that. If you drop an egg, right, it breaks. If you drop it into the floor, it breaks, and we never see the egg spontaneously come back together into a whole egg. We never see any of that, right? Your office desk gets dirty, but it never gets clean. So what's going on? Why is it that there's always one direction, right, and never the opposite direction? So let's understand that more carefully. The common denominator, if you've the common denominator among the examples I just gave, right? The egg that you throw and breaks and never comes back to an egg, and the cube that melts and never comes back to and never forms back to be a cube in the water, is basically if the common denominator is something that starts in a state which is organized, structured, and ordered, an ice cube, a clean desk, and a whole egg, and then ends in a state which is less organized, less ordered, and let's say more random and less chaotic, right? A broken egg and a dirty desk. So quite simply, at least entropy can be defined as this natural tendency. This is a natural tendency in our universe for systems to move towards disorder, right? You start from something which is more ordered and more structured, right? And you move to something which there is more disorder in it, right? Think again of an egg that breaks and never comes back to an egg. So that is what really entropy is, this natural tendency for systems. And entropy is this, and also a measure. It also gives you a number that measures how the amount of disorder or chaos in a system. So if you drop a deck of cards, let's take another example. If you drop a deck of cards to the floor, you don't see it reorganizing itself again, right? You drop it, the cards in the deck remain unordered, right, and never comes back again to be an ordered deck of cards. That's another example. And so it's really this phenomenon of disorder, right, of natural tendency of systems to move towards disorder can be made more accurate with what we call the second law of thermodynamics, right? The second law of thermodynamics explains this sort of nature's tendency to move towards a state which has lower energy. And not in the opposite direction. Think of the ice cube again, right? The ice cube is cold. You put it in a hot bowl of water. It's hot. So what's going on? There's some thermal energy here. Heat is like some form of energy. It's like thermal energy. And the second law of thermodynamics tells us that thermal energy or heat moves from regions which are hotter, which have higher temperature, to areas where it is colder and have lower temperature. This is nature's way to think of being fair. So that is that's the reason why, for example, the ice cube melts and never see it again, forming into a whole cube in the hot bowl of water. So this energy involved here, right? If we now think about it, heat is transferred from the hot water to the ice cube. The ice cube is colder, the water in the bowl is hotter, and so heat is transferred. Thermal energy is transferred from the water to the ice cube, and thermal energy now spreads out evenly, right, between the glass, between the hot bowl of water and the ice. So there's a thermal spreading here of the heat is even now, right? There's no, after a while, there will not be something colder, nothing hotter. There will be, everything will have the same amount of heat, the same temperature, basically. And that means that the energy is spread evenly among the bowl of water and the ice, now that it has melted into a liquid, right? And so that also explains why broken eggs do not spontaneously form into whole eggs, and why your office desk is not going to clean itself, because that will contradict the second law of thermodynamics. So the lesson here is that objects with higher temperature have higher entropy than objects with lower temperature. Entropy measures the amount of disorder or randomness in the system, and nature seems to have this tendency to increase disorder and increase randomness in the system. And according to the second law of thermodynamics, which is a very fundamental law in physics, the entropy of an isolated system always increases. Just keep that in mind. Entropy of an isolated system always increases and never decreases, right? And this has to do with heat being distributed evenly. And let me end with a quote of Sir Arthur Eddington, who says, the law that entropy increases always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. That is how fundamental the second law of thermodynamics is.
Okay, thanks for these interesting examples. But now that we learned that our office desk is unfortunately not going to clean itself, how can we relate this to the information paradox? So how would you define in a more rigorous way the concept of entropy? Could you maybe give us some insight into the statistical definition of entropy?
This is a brilliant question. Of course, we're going through the definition of entropy. But keep in mind, because we want to solve, to first understand, right, and then try to solve the black hole information paradox. That's why we're going through this. So keep that in mind. We'll get to that shortly. But to do that, we need another definition of what entropy is. What we just given is the macroscopic definition of entropy. We need another deeper definition, more statistical definition of entropy. Why entropy increases, right? Why does it increase? And to do that, quite simply, let's take another deeper look into the ice cube in a hot bowl of water example, right? What is ice? Ice is, as a substance, is a very solid object, ordered solid object. And this means, as we just explained, that it has low entropy. So what happens when the ice cube, as you put the ice cube into the hot bowl of water, what happens? Well, you probably know the ice melts. But what does it mean? What does it mean the ice melts? What happens? The ice cube is made out of what? Of molecules, right? And molecules are some arrangement of atoms. So you could have one molecule and you give me a different arrangement of atoms, specific arrangement of atoms. These are molecules, right? So now we observe the following. Ice is structured and ordered. We put it, the atoms of the ice do not have much room to move around. The atoms, that's why it's a solid, by the way. That's why it's a solid, because the atoms inside the ice do not have much room to move around. Now, that means that the atoms of the solid can only arrange themselves in very few different ways. There isn't a lot of room. There isn't a whole lot of room for the ice to move around. Ice has low entropy. Now, put the ice in a hot bowl of water, right? What happens? The molecules of the ice, what happens to them? They break loose, right? They become free, and the ice melts and becomes a liquid. And what happens? What about the molecules now, the atoms? Well, the atoms now acquire more freedom. They get more space to jiggle around. And what happens then? You know, the heat, that is the process where heat is transferred from the hot bowl of water into the ice. This happens. This sort of more freedom of the atoms inside the liquid, more room to move around, right, is another way of explaining why entropy always increases, why there's this natural tendency to move towards disorder. Because think about it again, very quickly. Ice is ordered. The atoms in the ice have do not have much room to wiggle around. You put it in a hot bowl of water, it melts, becomes a liquid. The atoms now have more room, more freedom to wiggle around, and therefore there is more orderings of the atoms, right? Now the atoms can arrange themselves, right? And there are far more possible ways for the atoms now to arrange themselves. And this is the way that entropy increases. It's because there is far more possible ways for the atoms to arrange themselves into. And that is a manifestation of why entropy increases and never decreases. That is another way of looking at entropy or defining entropy.
Fantastic. I think that was a very good analogy. Perhaps can you give us another example or more examples in which we can see this increasing freedom that you were talking about for the ice when it melts?
Yeah, so basically, if you ask me, well, Amr, what does more freedom for the atoms mean, right? You keep saying the atoms in the liquid have more freedom and more room to jiggle around than the atoms in the solid. Well, think about the ability of the water to splash around, right? You don't see ice splashing around, you see the water splashing around. This ability of splashing around, or sloshing, right, is basically the manifestation of the more freedom that was acquired by the atoms when the ice changed into a liquid. Yeah, right? I mean that is that, right? That is the how you actually see that freedom. So to make it even more precise, so we say that on the microscopic level, entropy is highly statistical and is rooted in the principles of probability. And let me even be more precise. Entropy is a measure of how much the atoms in a substance are free to spread out, how much freedom for the atoms to spread out, how much they are free to move around, how much they are free to arrange themselves in random ways. That is entropy. Higher entropy will always mean that there's greater freedom for the atoms to move around. And the more energy we have, the more atoms will move around and spread in different random ways, right? And so each such possible arrangement of the atoms is called a microstate. So to give you an example of what a microstate is. So keep in mind this sort of arrangement of the atoms inside a molecule. Each one of those is called a microstate of the system. If you know all the microstates in the system, you have complete information about the system, right? Complete information, and you have zero entropy, because the entropy is a measure of your lack of information. If you know everything about the microstates, all those sort of ways that the atoms can arrange themselves, if you know all of that as someone in the system, then you have complete information, and then the system has zero entropy. If you know nothing about them, then you have the entropy is maximal, is really at the top, right? And so this is the most fundamental definition of entropy. To make it even more clear before I end, let me give you a concrete example. Why do you all shuffle a deck of cards before playing a card game? What happens when you shuffle a deck of cards? Well, whether you know it or not, when you shuffle a deck of cards, you're maximizing the entropy of that system. So tell me why. Why are you maximizing the entropy of the system? Think of the system here, the word system, as the cards and the players of the game, right? When you shuffle the cards, you are maximizing, right, the entropy in the sense that all players now, we all want all players to have zero knowledge about the order of the numbers and the suits of the cards they are handed, don't we? Right? And that's the point. That's why we shuffle the deck of cards, because when we play, we do not want to know. We want to have as minimal information, maybe nothing, about the order of the numbers and the suits of the cards. Each possibility that of shuffling the card is a microstate. So how many ways, let me ask you this, how many ways are there, right, that you can order the 52 cards in a deck of cards? Well, there are lots and lots of different ways, right? Each possible way of ordering the 52 cards in a deck of cards is what I keep calling, is what is called the microstate, right? That's called a microstate. There are many, many different ways. You keep in mind that all these microstates describe the same deck of cards. There's only one deck of cards, but there are many possible ways to arrange the 52 cards in the deck of cards, and that's called the many microstates, right? And all of them have equal chance. All of them have equal chance. When you shuffle the deck of cards, you don't care. It is going to be a specific order. Each time you shuffle, that's one order. You shuffle it again, that's another way. You shuffle that a third time, that's another way, right? And in this sense, and this is what I'm going to end, entropy, whenever you hear the word entropy, it is the count. It counts the possible number of orderings in a given system. In this case, a deck of cards, the possible number of microstates available in a given system. The more the microstates, the more there's possible orderings, the higher, the larger the entropy is. And nature has the tendency to increase entropy, right? By that we mean is that the number of microstates available in any given system always increases. And so keep that in mind. If you tell me, whenever you hear the word entropy, that means what does it count? And how many microstates are there? What are these possible orderings available in the system? So keep that in mind. So that is the definition that we're going to use in the understanding the black hole information paradox.
Okay, so thanks for defining those two important ingredients of the black hole information paradox. But how can we connect our understanding of entropy and our understanding of black holes with each other. So what is the entropy of a black hole? Can we also just count microstates of a black hole, or what is the idea behind it?
That is the billion-dollar question. So we just went through a description of what black holes are and defined entropy in two different ways. Now we want to relate all of this to define entropy of black holes. Do black holes have entropy? Well, if you've been paying attention, I started this lecture by saying that black holes are believed to have what? Zero entropy, right? And then zero entropy, now we understand better. Zero entropy means, from the perspective of someone sitting outside the black hole, meaning that you have complete information about the black holes. You have complete information because there's no uncertainty. And that is zero entropy. And if you go back to the ice cube example, something which has zero entropy, has zero temperature. So is there any way that we can, here's a question, right, that physicists ask, is there any way that we can, instead of saying that black holes have zero entropy, to say that black holes have entropy? Is there any way to give black holes entropy other than just saying that I know everything about the black hole and have zero entropy? To actually understand that, let us see how black holes form. A black hole usually forms from a collapsing star. Stellar black holes form from a collapsing star. The core of a collapsing star dies and forms a black hole. And so let's ask, what is the entropy of a star? Well, a star is super hot, super dense gas. With how many atoms? Oh, God knows. Trillions and trillions and trillions, many, many, many atoms. Are they randomly moving? They are randomly moving. It's a gas. So how many possible ways can these astronomically high number of molecules in the star arrange themselves? How many ways can they arrange themselves? Oh my God, again, an astronomically large number. So that means what? Low entropy or high entropy? Well, that means high entropy because there's so many different microstates and ways that the atoms in a star can arrange themselves, right? The number of those microstates is the entropy. Entropy measures that. Okay, now I'm sitting outside the black hole. I'm looking at the star, and I'm an external observer. And then there's an instant where the star collapses and forms a black hole. Oh, so now the star forms a black hole. If you have been paying attention, if you are sitting outside the black hole, what is it that you only need to know about the black hole? Remember the no-hair theorem? You only need to know mass, the electric charge, and the momentum. You don't need to know everything that went in the black hole. You don't need to know that. If you know all these properties, you know everything about the black hole. But now, if you know everything about the black hole, is there any uncertainty? No, because you know everything. So what does the black hole entropy is? Well, zero. What was it before it collapsed? The star. Oh, it was very high because it has many, many, many atoms moving around. So all of a sudden, I go from a state which is very, very high entropy to a state which is very, very, almost zero entropy. Complete information, zero information about the system, the star, yeah, zero information about the star, to complete information about the black hole. Well, does that ring a bell? Of course, that you tell me, Amr, the second law of thermodynamics always says that entropy always increases. It never decreases. How can you tell me now that I go from a state where the star, which had very high entropy, to a state of low entropy, which is a black hole? That doesn't make any sense. This violates the second law of thermodynamics. Correct. And remember the quote of Sir Arthur Eddington, right? If your theory is against the second law, I can give you no hope, and it's going to collapse into deepest humiliation. So this is really what led the scientist Jacob Bekenstein, right, to whom we see the picture right now on the screen, to maybe think that there is a deep connection between black holes and entropy. Is there anything that can be done to save the second law of thermodynamics? We do not want our theory to oppose or contradict or violate the second law of thermodynamics. And he made a brilliant observation. The brilliant observation goes like that. The surface area of the black hole, right? The black hole is a region. So think of a black hole as a three-dimensional region, a sphere, right? It has a boundary. right? The boundary has surface area. According to the general theory of relativity, written down by Albert Einstein, the surface area of a black hole always increases. Oh, it never decreases. You say, but you just told us that there's entropy always increases as well. So perhaps there is this connection between entropy and the surface area of a black hole. Both are quantities that never decreases, always increases. So is this the way that one can say entropy, give black holes entropy instead of saying it is zero? Is this the way that can maybe we save the second law of thermodynamics and say that black holes have entropy instead of zero entropy? We'll see.
Wow,
So,
very fascinating new concept, and also beautiful equation that we can see now. Looks very simple and neat. But earlier you said that the most fundamental definition of entropy would be in terms of counting microstates. We spent some time describing what microstates were. So what does this entropy that we see on the screen now count for a black hole?
yes, so that's another excellent question. Jacob Bekenstein, actually, in his work, first of all, he was able to realize that black holes behave in a way that is very similar, that sort of obeys, the behavior of the black holes obeys the traditional laws of thermodynamics, the laws which govern the behavior of thermal energy, heat, and entropy in the motion. And actually he discovered black hole thermodynamics, but he didn't stop there. Why? Because if you remember, the most fundamental definition of entropy is in terms of what? Is in terms of statistical. It's statistical in nature. That is to say, you need to tell me, what does the entropy count? How many microstates does it actually count? That is the deeper definition. And in fact, Jacob Bekenstein sought a more deeper definition of what black hole entropy is. So a definition that actually tells us what microstates does the black hole entropy count, and what are they? Well, that's what he did. And so to actually, and I want you here, before I get to actually what Jacob Bekenstein did, to remember the deck of cards. We always want to know how many ways is it that you can arrange the 52 cards in a deck of cards. Once you know that, you know the number of microstates in your system. So at this point, I'm going to keep mentioning the term information. I repeat it many times. And right now, it's really helpful to think of the term information in terms of, one of two ways. Either the positions and the momenta of all the particles of a body that's going to the black hole. When a body goes into the black hole, whether it's a book, whether it's a chair, whether a human being, right? Your bodies, they were collections of molecules and atoms connected together, right? So that is what sometimes what's people call information about an object. But it's helpful now to think of an object as a set of ones and zeros. Think of your binary code. Think of your code in your information as they are stored on electronic devices. They are stored into ones and zeros. If you were to take a deeper look into files stored in the memory of your electronic devices, you would see some ones and zeros. So now let's imagine what, like Jacob Bekenstein did, we build a black hole. How do we build a black hole? Let's imagine you have a sphere, right? And we keep throwing, like we have right now on the screen. And we want to throw cubes, right? We imagine an object that falls into a black hole is made of like cubes, tiny, extremely tiny little cubes. So I have a sphere, and I'm going to stuff it with little cubes, and you know cubes. Well, each cube has a 3 sides, right? So tell me how big the size of the cube? Well, they are extremely tiny, and the length of each side of the cube is actually smaller than you can ever imagine. It is equal to what is called the Planck length, And if you look at the screen right now, What is the Planck length? It's 1 over this huge number, which we have 35 zeros in the denominator. That is what is called the Planck length in meters, right? So imagine a cube which has 3 sides. Each side has a length of what we call the Planck length, 1 over 35 zeros. That's a cube, right? And then I'm going to assign to each cube a 1 or a 0, a 1 or a 0, just like a code, a binary code. And I'm going to imagine I have such cube. Okay, but now, remember Jacob Bekenstein observation that the area always increases and as the entropy always increases. So now instead of imagining maybe cubes, we can imagine a square instead of just a cube, right? And now, if you look in the screen, the surface of imagine this is a black hole. It's like a sphere. The surface area has what? Many squares. So suppose you look at the sphere and you split it all in tiny little square. Each square has a side of the Planck length. And by the way, the Planck area now, right? See, it's 1 over about 70 zeros in the denominator. That's how small the cube is. So imagine you have the sphere, which is a black hole, and on the surface of the black hole, there's tiny little squares. And in each tiny little square, you're going to have a 1 and a 0. Okay? So what is the entropy of a black hole? He thought, well, the entropy of a black hole then must be a count of what? A count of the number of those tiny little squares on the surface of the black hole, right? We always said that the entropy counts stuff, counts, right? And so if I divide the area of a black hole, no matter how big it is, I have an area of the black hole. I divide it by the size of each square on the surface of the black hole. What do I get? I get the number of those tiny little squares, which called Planck area, which each square has a Planck area. And with that, I get the number of squares, I get the number of microstates, and hooray, I now have a statistical definition of the black hole entropy because he was able to give you what exactly the entropy of the black hole counts. And to give you an estimate, let's estimate the entropy of a supermassive black hole, Sagittarius A star in the center of our Milky Way. Let's count the number of those tiny little squares on the surface of the supermassive black hole. How many squares are there? If you plug in all the numbers and the size and the dimension of the size of the Sagittarius A star, you get something like 2 to the power 90 Planck squares. 2 to the power, take that in. Take a moment to absorb that number. 2 to the 90 Planck squares. That is how big, that's what we call information. That's what we call entropy. So the number of those squares is the entropy or the number of microstates of in this case, in this example I gave you is the Sagittarius A star. Now, the astonishing thing, really astonishing, is that a year later, Stephen Hawking confirmed this connection between the ever-increasing surface area of a black hole and entropy in a way that was very different from what Jacob Bekenstein did. A very clever calculation by Stephen Hawking, a very thorough calculation. He was able to confirm that really, it's a calculation that really the black hole entropy, right, varies as the surface area, the surface area of the black hole. If we go back to the previous slide, which I didn't really comment on, see, even the one with the Jacob Bekenstein, let's take a look again at this equation. This equation says that I have the entropy, which I denote by S, the area, and then what's down there is the size of each little cube. That's called LP times LP. That is the size of the cube. And this was confirmed by Jacob Bekenstein. This was first derived by Jacob Bekenstein and confirmed by Stephen Hawking in a very thorough and clever calculation. So Hawking then confirmed this connection, but he also showed us that black holes radiate and black holes have temperature, and the stuff that goes into the black hole is not doomed. Is not doomed. it has a chance of coming out again. That was astonishing. That was really, really surprising, because everybody thought before Stephen Hawking that if stuff goes in, there's only one way to continue all the way down to the singularity. You never have a chance to actually go. He actually showed us that no, black holes radiate and they have temperature. And if they have temperature, what do they have? Think of the ice cube. If something has temperature, then it must have what? Entropy. Entropy. So all of a sudden, the conundrum that we violate the second law of thermodynamics when you go from a star, remember, a star has very high entropy, to a black hole which has zero entropy? No longer true. Black holes have temperature. Black holes have entropy. The entropy is all on the surface of the black hole, the area, right? So no more contradiction to the second law of thermodynamics, no more violation. Or as Sir Arthur Eddington said, no more humiliation of theory. Your theory will not be humiliated, because now, even if we go from a star that collapses to a black hole, the star has an enormous amount of entropy, while the black hole also has an enormous amount of entropy. Remember, a supermassive black hole, it has 2 to the 90 of those number of squares. It counts those squares, and that's a huge, an enormous amount of entropy. So we're good to go. Our second law of thermodynamics is good.
Wow, those are mind-blowing numbers that you just quoted. Well, we saved thermodynamics, which is great, but it looks like that there's even a bigger problem now arising. So Hawking radiation, as it's called, radiates away information. And what happens then with quantum mechanics? Don't we have
my God.
Are we not saving one thing and then creating another problem?
Yes, an even bigger problem, as a matter of fact. It's even more serious, this second law of thermodynamics, and it's what's called the black hole. It's known as the black hole information paradox, and it's one of the biggest unsolved problems in all of physics, right? And we'll see why now. What is the problem? You tell me, okay, why is it that when you tell me stuff that goes inside the black hole, if I jump into a black hole, or I fall into a black hole, I have a chance of surviving. Good, I'm not doomed. I'm not gonna be crushed all the way to the singularity. I have a chance of going down. Isn't that a good thing? Well, we'll see that it's not really a good thing. Because of quantum mechanics. So let me give you an example of what it means for Hawking radiation to destroy information. The problem is Hawking radiation destroys information completely about the object, any object that falls or crosses the boundary of the black hole, the event horizon of the black hole. What does it mean to destroy information? Remember, I told you earlier that when the word information here, think of ones and zeros. Think of ones and zeros on the surface of the black hole. Think of a square with 1 and a 0. That's what I want you to sort of maybe have in mind now when I say information. So how is this information destroyed? How does Hawking radiation destroy information? Let's take an example. So if I have a die has 6 faces, and each face has what? A number from 1 to 6. You know that when you throw a die, it's a perfect die, it doesn't have any flaw, you know for sure that it will land on any one of those 6 faces, 1 to 6. You don't know a priori which number it will land on, but you know it must land on any one of those numbers, 1 to 6, right? So although you don't have any information about which one number it's going to land on, you know it's there. The information is not lost because it's going to land on 1 to 6. But now you throw the die, and it lands on an empty face. Empty face. What does that mean? Empty face. Oh, stop. What happened? The information about a number, well, I don't know which number, 1 to 6, is lost. It's gone. It's an empty face. But does that make any sense to you? For information to just disappear like that? To say that one of the numbers on the faces of the die just disappeared? Well, it doesn't make any sense. And that's why it's problematic. And that is the sense, maybe, so that Hawking radiation destroys information when the black hole evaporates, right? Because that's what Stephen Hawking showed us. The black hole evaporates. At some point, the black hole is going to disappear. And when the black hole disappears, all the information that went inside the black hole is gone. It's destroyed. It's not there anymore. And quantum mechanics that forbids that. Why is quantum mechanics? Why are you making a big fuss about quantum mechanics? Well, the principles of quantum mechanics, since now for almost 100 years, right? It is the framework, the laws of physics that govern the subatomic world. And this is a very successful theory. It's been tested so many times, and you do not want to contradict a very successful theory. The principles of quantum mechanics tell that there's a principle, a foundation of quantum mechanics called the conservation of information, the conservation of probability, right? And the Hawking radiation, when the black hole evaporates and stuff has a chance of getting out from a black hole, the information is destroyed. Quantum mechanics is very mad. That does not sit well with quantum mechanics. Quantum mechanics forbids that. Quantum mechanics says that information must always exist at all times, forever, regardless of whether it's hidden or inaccessible. Remember, when stuff goes into the black hole, it's not erased from existence. It just becomes hidden. What Hawking said, that when the black hole evaporates and ultimately it's going to shrink, all the stuff there is erased from existence. It's no longer even hidden or inaccessible. And that is a problem. That is what is known as the black hole information paradox. Probably the ultimate solution to the paradox will be, at least according to what the majority of very notable theoretical physicists believe, is to have a complete theory that unites the general theory of relativity and quantum mechanics, what we call a quantum theory of gravity. That may be where the ultimate solution to the problem is, which we still do not have. So you ask me now, is there any way out of this black hole information flux? Are we doomed? Well, fortunately, there appears to be one, and now we talk about the holographic principle.
Very exciting and mind-blowing stuff. So is there a way to, you seem to promise that there's a way to make quantum mechanics happy. You mentioned earlier that there's this information on the horizon. Does that have anything to do with the potential solution?
Yes, in fact, that should give you a clue. Thank you for asking that, Goncalo. In fact, that should give us a clue that of what we call the holographic principle, right? That the entropy of a black hole, the Bekenstein-Hawking entropy, is proportional to the surface area of the black hole, not its volume. Well, first of all, you'd ask me, Amr, maybe this has only been worked for a black hole. A black hole is a region of space-time, you remember, that has extreme and intense gravitational field. Is this true for any region of space-time? Think of the sun, think of the earth, think of anything that occupies a volume, any object that occupies a volume in three-dimensional space. Can we say that it has entropy, right? And this entropy is bounded. It also is proportional to the area, not the volume. Yes, indeed, because it's another region of space-time, except that this time, because this region of space doesn't have this extreme, immense gravitational field like a black hole, the Bekenstein-Hawking entropy will be like the maximum amount of information that one can store in the volume. So you can give me a volume of space-time. How many stuff? What is the maximum amount of information that I can store inside the volume? Well, it is proportional to the area of that volume. Why is this odd? Why is this odd? Why is this an unusual idea? Because the amount of information in a volume, it makes more sense to say that if I want to store more information in a volume of space, right, that is made out of very little cubes of tiny size, that I just increase the volume. So the amount of information in the volume increases with the volume, not with the surface area. The larger the volume, the more the information, except that Bekenstein and Hawking told us, no, the maximum amount of information that you can store, those cubes that you can throw, those tiny little cubes that you can throw, the maximum amount of those cubes, no, it's not proportional to the volume, it's proportional to the area. And this is really surprising result. And this is the clue that our universe is a holographic principle. So let's really see what holographic means. It's really mind-boggling. Remember, the boundary of the black hole is one dimension less than the volume. So if you think of a sphere, right, we talk about the volume of a volume of the sphere and the area, right, of the sphere, right? So there's one less dimension. So let's assume. It was years later, right, that this idea of holographic space-time, the holographic principle, was that Bekenstein-Hawking entropy inspired Gerard Ittelf and later Lenny Susskind, to really suggest that maybe the information of all material that fell into a black hole, here is the Gerard Tuft on the left and Leonard Susskind on the right, that anything that goes inside the black hole, all the information, all the ones and zeros, remember the every object, a book, a chair, a human is made of ones and zeros. So that inspired them to say that the material, the information, or all the material that fell into a black hole could somehow be captured on the body of the black hole, encoded on the event horizon of the black hole. Remember, the boundary of the black hole is the event horizon, right? So the information, or the sets of ones and zeros that we see on the screen, that is stored on the boundary. So now it's like an image. It's like an image stored in the memory of our electronic devices. Remember, when you have an image file, like a video or a sound file, right? It's stored in a compressed format, right? It contains information. So think about this sort of image that you see on the screen, this stuff on the surface of the black hole. These are ones and zeros. This could be encoding information about a book. This could be encoding information about a chair, about a laptop, about a human being. It's many combinations of ones and zeros, right? So they say maybe that as stuff falls into a black hole, the information about the ones and zeros of that object is stored, is captured, is encoded on the surface of the black hole. And this is not a weird idea. This is known usually as the holography or holographic principle, or, you create a hologram. You have a two-dimensional surface, in this case, the surface of a black hole. Think of a sphere. It has a two-dimensional surface, and it knows everything about the three-dimensional interior of the volume. So anything about the volume, anything that happens inside, right, is encoded on the two-dimensional surface, right? And this is usually the idea of a hologram, right? What is a hologram? It's simply a three-dimensional construction of an object, right? You give me an object, I record information about that object, and then I create a hologram of the object. So in this case, by a process called holography. So holography, think again of the sound file or image file or movie file, right? If I give you a sound file or an image file or a movie, right, of your favorite movie or favorite song, MP3, MPEG, something like that, and when I hand you that, you don't see in the file, it's ones and zeros. Do you see the singer? Do you see the actors in the movie? You do not. But it's a bunch of ones and zeros. Once you play that file on your cell phone or your laptop, all of a sudden you see the singer in your favorite song, the actors in your favorite movie. The software in the computer has done what? Reconstruction of the song, the singer, the movie, the actors. They have been reconstructed from what? From the file, right? From ones and zeros. Holography on a hologram is like that, except that I store information on a two-dimensional surface, but that contains everything about the three dimensions. And as a matter of fact, to say one more thing, it was Leonard Susskind, after Gerard Tuft, who showed us, right, how this encoding can happen. You ask me, Amr, these are all theoretical ideas. Okay, maybe it's all theory, all argumentative. No, well, Leonard Susskind told us that how this encoding, this encoding on the surface of a black hole can be done using what is called, a very famous theory called string theory, right? It's a theory of, candidate theory of quantum gravity. He told us how to do that. And it wasn't until 1997 when Juan Maldacena actually worked out using mathematics of string theory, very, very detailed calculations. First, I would say the first concrete example of what is known as the holographic principle, using the mathematics of string theory, that our existence, everything is encoded on an infinitely far away two-dimensional surface. So I have a two-dimensional surface. It's very, very, very distant, very, very far away, that knows everything. It contains ones and zeros on the surface, and these ones and zeros the sets of ones and zeros know everything about what happens inside. I don't need to go inside to know what's going on. I just need to look outside, take a look at the binary code, decode the binary code, and I will know everything what goes inside. That is the idea of holographic space-time. That is the idea of the holographic principle, which has been worked out by Juan Maldacena in 1997 as the first concrete example. And let me tell you, this is when really and seriously people started to believe in the idea of holography and the holographic principle in 1997.
Wow, that is mind-blowing. So I think the question we all now have, does the holographic principle solve the black hole information paradox?
Very good question. And I would say it at least gives you a framework to solve the black hole information paradox. In what sense? It gives you a way out. In what sense? Because as we just said, so imagine an object falling into the black hole. Any object you can ever think of, right, contains ones and zeros. As the object falls into the black hole, the ones and zeros of that object are captured on the boundary of the black hole, right? And by the holographic principle, then, it knows everything about what's going inside. So let's assume now the black hole evaporates. Let's rerun the scenario of Hawking radiation, black hole evaporation. Now is the time, now the black hole is evaporating. Information inside the black hole is coming out. That's what Stephen Hawking taught us. That's what he showed us, right? Now information is coming out from inside the black hole. Is the information erased? Well, previously it was thought it was erased. What about now with holography? Well, I just told you. As the object is falling inside the black hole, the ones and zeros of the object, the information about the object is now where? Well, on the surface of the black hole. So it doesn't matter if the black hole evaporates. It doesn't matter whether it radiates or not, because the information is there on the surface of the black hole. So that is the sense that the black hole information paradox is actually solved.
Wait a second. So is that a solution to everything? Can we all go home happily after this, and should we stop funding research for this?
Well, I wish you didn't ask over. So I can only wish so, but unfortunately, no. So let me tell you why. Although the holographic principle gives us a hope, gives us a way out of solving the black hole information paradox, it does not yet tell us exactly how the information from inside the black hole escapes. It doesn't tell us exactly what the Hawking radiation carries away with it. How is it that the information, when it escapes from the black hole, actually where? And where does it go? Right? It doesn't. We don't know that yet, even until today, and that is the subject of intense research. But wait a minute, hang on. We will learn more about the details of the specifics of how information of the solution of the black hole information paradox in the next 3 lectures. And there's another problem. There's another thing I would like to end with, is that the problem that is the concrete example that has been worked by Juan Maldacena is a holographic description of not our universe. It does not really describe our physical universe, a physical 3-dimensional universe. It does not, right? He worked out an amazing example, very concrete, very specific, but it does not describe our physical 3-dimensional universe. And scientists have been working actively to make it work for our own universe. But let's assume for a moment, this is the last thing I'll say, that scientists, physicists, have successfully found a holographic description that works for our own physical 3-dimensional universe. Suppose we have that in mathematics. Then I'll leave you with the following question to ponder over. Are we holograms? Is everything around us a hologram? Are we living in the interior of some space where the reality is infinitely far away on a distant 2-dimensional surface? Is the entire physical existence as we live it as we experience it, as we perceive it, nothing but some reconstruction of reality that exists on a distant two-dimensional surface? Well, we'll have to wait and see. Thank you.
Fascinating last sentence there. I think it's very quotable, sounds like a movie line.
Yes, it is.
So on the screen, you can see now some references of extra material that in case you want to take a closer look at this fascinating topic. Thank you everyone for tuning in and listening to the episode Black Hole Wars #2, Return of the Susskind. We hope you enjoyed it. Next up, you'll have the third episode tomorrow called A Curved Hope, in which we will delve deeper into what it means to recover information from a complex system. We will consider everything from everyday situations to black holes. And we will also discuss a fundamental difference between the information we are used to and the information in quantum systems. Hope to see many of you tomorrow for one more exciting discussion.
Thank you. Thank you, Roger. Thank you, Goncalo.
Thank you, Amr.
Thank you so much.
Thank you very much.